To think about the next time you ask your phone a question. Until next time, keep questioning the ghost in the machine.
You know, usually when we think about reading a simple text message, right? Something like, hey, I left it on the table, we treat it like a simple file transfer.
Right. Yeah. Like it's just moving data.
Exactly. You view it as just beaming a string of data from one phone to another. It feels, I don't know, mechanical, sender to receiver, a perfectly closed loop.
Which is, it is the ultimate illusion of modern communication. We assume that because the transmission of the data is binary-like, the text is sent, the text is received.
Mm.
The comprehension of that data must also be this simple mechanical process.
But if you actually stop and think about what your brain is doing in that exact fraction of a second, I mean, it is staggering.
Yeah, it's computationally massive.
Right. You have to know who I is, which means, maintaining a persistent mental model of your relationships. You have to infer what it could possibly be based on a conversation you might have had like 3 days ago about a missing set of car keys.
Yep.
And you have to know exactly which table in the physical universe they are referring to. The coffee table, the dining table, the table at the restaurant you just left.
Exactly.
Suddenly, that simple data transfer looks a lot less like a mechanical sorting of symbols and, well, a lot more like mind reading.
It is cognitive telepathy. I
Yeah.
mean, we perform this telepathy seamlessly, effortlessly, every single day, without ever stopping to realize just how mathematically and computationally impossible it really is for a system that doesn't possess a human mind.
And that impossibility is our mission today. Welcome to the deep dive into the source material. We are embarking on an extremely detailed, logically structured, and rigorous academic journey into the actual mechanics of human language and artificial
The
intelligence.
big one today.
It is. We are basing our entire exploration on a profoundly dense and illuminating text, which is Chapter 14, titled Inference in Language 2.
It's really a phenomenal piece of cognitive science writing
Yeah.
because it forces us to look under the hood of our own minds. It strips away the magic of language and forces us to look at the gears.
And we are setting the stakes very high for you today. You interact with so-called intelligent language models every single day. Your phone finishes your sentences, chatbots draft your emails, virtual assistants schedule your meetings.
Right, and the tech industry tells you that true artificial intelligence is just one software update away.
Exactly. But we are going to reveal the profound, invisible cognitive architecture that you use just to understand a simple sentence. We are going to explore the underlying logic, the causality, and the fundamental mechanisms of language to show you exactly why machines are fundamentally trapped outside of that architecture.
We are going to be dissecting language step by step. So you'll start at the atomic level of syntax, build our way up into semantics, cross the vast chasm into pragmatics, and ultimately confront a very specific, crucial concept called abductor inference.
Right.
It is a heavy philosophical journey, but understanding the precise mechanics of these concepts is really the only way to truly understand the grand illusion of modern AI.
So the text introduces a brilliant visual metaphor for how language is constructed, calling it the inverted pyramid of language understanding.
Yeah, I love this visual.
Right. Imagine a pyramid balanced on its absolute tip, expanding outward and upward as it grows. The very bottom, the point resting on the ground, is orthography.
Orthography is the raw, physical substrate of written language. The letters, the punctuation marks, the spaces. If you are a computer, this is just a string of ASCII characters or Unicode. It is purely symbolic.
So we are just talking about the shapes of the letters, like the vertical line and the horizontal line that make a T.
Exactly. And then, moving slightly up the pyramid, those raw symbols cluster together to form lexical and morphological features. The letters form words, prefixes, suffixes. You get parts of speech.
Yeah, okay.
So the letters C, A, and T form the noun cat. The letter S added to the end makes it plural.
And this is where we hit syntax, right? Because once we have those lexical features, we start chaining them together.
Yes, syntax is the mathematical engine of language. It is the set of rules for combining words into phrases. We take a noun phrase, like the ferocious lion, which contains a subject and an adjective.
Okay, yeah.
Then we add an action, a verb. The ferocious lion devours. If that verb is transitive, meaning it requires something to receive the action, we add an object. The ferocious lion devours meat. We now have a complete grammatically sound sentence built entirely on syntactic rules.
And a computer handles this bottom section of the pyramid flawlessly. In fact, I mean, it handles it better than we do.
Oh, absolutely.
Because syntax is just a set of deterministic rules for combining symbols. It's algebra.
Right, it can be processed, analyzed, and generated by a machine with incredible speed. You can build a parser that diagrams that sentence in a microsecond, identifying the subject, the verb phrase, the dependent clauses.
But as we keep moving up the inverted pyramid, the architecture changes. Sentences form paragraphs that express a unified topic. Multiple paragraphs join together to form a narrative, which linguists call a discourse or a text.
Exactly.
Yeah.
We are moving from a single sentence about a lion to an entire chapter of a National Geographic article.
And at the very top, the widest, most expansive part of this inverted pyramid, you have fully open-ended conversational text.
Which is where the famous Turing test sits.
Right. And the wider the pyramid gets, the more meaning is encountered. And as the text points out, this is exactly where computational treatments of language start to fail catastrophically. Because language leads a double life.
It really does.
Yeah.
It can be viewed purely syntactically, just rules for combining characters. But the second life of language is a journey into meaning. Natural languages use those symbols to convey something about the real world. A children's book takes this same journey into meaning as a dense Russian novel.
Okay, let's unpack this for a second, because I want to challenge this separation between syntax and meaning, because I think it's where a lot of our assumptions about AI come from.
Okay, let's hear it.
If meaning is just the result of combining words, isn't meaning naturally going to emerge from perfect syntax? Let's say I program a computer with a flawless dictionary database. It knows the exact definition of every single word in the English language.
Right.
And I give it a perfect algorithmic map of English grammar. If it executes the grammar rules perfectly and it cross-references the definitions perfectly, doesn't it naturally mathematically arrive at the meaning of the sentence?
It is the most logical assumption to make in computer science, honestly. And it was the foundational assumption of early AI research.
Yeah.
But it is fundamentally flawed.
Really? Why?
To prove why, the text brings us to the concept of semantics, the study of what things actually mean. To understand semantics, you need knowledge and belief about the physical world, not just syntax and dictionary definitions. The author asks us to consider a very specific, seemingly simple sentence. An alligator can run the 100-meter hurdles.
Okay.
An alligator can run the 100-meter hurdles. Right. How do you parse the meaning of that sentence? If we use your theoretical computer model, it looks at the syntax. Subject, alligator, modal verb.can, main verb.run, direct object.hurdles, modifier .100-meter. The syntax is flawless.
Right. Perfectly grammatical.
And it looks up the definitions. Alligator, a large semi-aquatic reptile. Hurdle, an upright frame that an athlete jumps over in a race.
So the computer has successfully mapped the data.
But has it understood the meaning? Knowing that alligator is the subject and run is the verb tells you nothing about the physical reality of the scenario. To actually understand that sentence, you have to mentally simulate the physical act of an alligator attempting to run a hurdle race.
My brain immediately goes to a biological reality check. I'm picturing an alligator's body shape. It's incredibly long, very heavy, and it has these short, stubby little legs that splay out to the sides.
Exactly.
The center of gravity is practically dragging on the floor.
See, you are accessing your world knowledge. You are building a three-dimensional model in your mind. You're placing the alligator on a track. You're placing a tall, upright hurdle in front of it. And you are trying to compute the physics of those short legs, generating enough upward thrust to clear the obstacle.
And the conclusion is it's absurd. The physics don't work. The sentence makes grammatical sense, but semantic nonsense.
For a human being, even a young child, this requires almost no active processing time. You just visualize it and you instantly know the physical absurdity. The crucial point here is the mechanism of that realization.
Right.
The answer to whether that sentence makes sense is not located in the syntax. It is not in the dictionary definitions. It requires a cognitive leap called inference to apply real-world knowledge to the symbols.
So the meaning isn't contained inside the words themselves. The words are just triggers. They are instructions that force the human brain to build a simulation using our own lived knowledge of gravity, anatomy, and physical space.
The words are merely pointers. If a computer system doesn't know what an alligator's legs actually look like in physical space, how much an alligator weighs and how gravity affects mass, it can parse the grammar of that sentence all day long and still have absolutely zero comprehension of what the sentence means. It hits a semantics wall.
Wow. So if a single standalone sentence about an alligator requires us to possess a vast internalized database of physical world physics just to understand its basic meaning, what happens when we start stringing sentences together into actual conversation?
It gets much, much harder.
Because we don't just walk around stating isolated facts about reptiles, we interact, we have motivations.
Right. When we move from isolated sentences to interactive texts or conversations, we left the realm of pure semantics and enter a much more complex field called pragmatics.
And pragmatics is the study of how context affects meaning. It includes the person making the statements, their purposes, their interests, their intent. It covers sarcasm, irony, jest, and implication. In pragmatics, the literal, word-for-word definition of what someone says is almost never what they actually mean. Let's look at the classic example from the text. We are sitting at a dinner table, the food arrives, and I look at you and say, "Can you pass the salt?"
A totally normal question.
Right. But if you are a machine operating on pure syntax and literal semantics, you parse that as an inquiry about your physical capabilities.
I would evaluate my physical state, note that my arms are functioning, recognize that the salt shaker is within my grasp, and I would reply, yes. And then I would continue eating my food without moving the salt.
Which means you answered my yes or no question with absolute flawless accuracy.
But I completely failed the pragmatics of the situation. I failed to infer your intention, which was a polite request for a physical action, not a medical inquiry about my upper body mobility. The context, your purpose for speaking, the social norms of a dinner table, the shared goal of seasoning our food, is totally invisible to a purely semantic parser. This feature of ordinary talk makes language interpretation computationally devastating for artificial intelligence, but it is as natural as breathing for people.
This pragmatics problem isn't a new discovery either. In fact, Alan Turing, the godfather of computing, recognized this exact limitation decades ago when he first conceptualized how a machine might attempt to simulate human thought.
Yeah, Turing was way ahead of his time on this.
The text looks closely at Turing's original exposition of the Turing test, where he uses Shakespeare to prove this exact point about context and mental states.
It is a profound dialogue. Turing imagines a human questioner called the interrogator, testing a computer called the witness. The interrogator wants to see if the machine actually understands human context, so he asks the computer about Shakespeare's famous Sonnet 18. Shall I compare thee to a summer's day?
Let's walk through the logic of this test step by step, because it isolates exactly how language works. The interrogator asks the computer, why not use a spring day instead?
And the computer replies, it wouldn't scan. It means that the phrase, a spring day, breaks the iambic pentameter rhythm of the poem.
Right.
This is a brilliant but ultimately syntactic structural answer. It proves the computer has a specialized mathematical knowledge of how sonnet meter is constructed.
But the interrogator doesn't stop there. He pushes deeper into the realm of meaning. He says, okay, how about a winter's day? A winter's day scans perfectly. The mathematical rhythm of the iambic pentameter is perfectly maintained.
Now the focus shifts entirely away from syntax. Computer answers, yes, but nobody wants to be compared to a winter's day.
Which is such a striking response for a machine to give.
Because it requires assumptions about the subjective human experience.
Yeah.
What are the statistical associations an AI might make with winter? Cold, snow, December, short days. But to answer the question correctly, the system has to understand how those physical realities translate into emotional weight. It requires knowing that winter feels barren, gloomy, or harsh, and knowing that a human being experiencing the intense, blossoming state of romantic love would never choose that specific emotional imagery to describe the object of their affection.
Because summer represents warmth, vitality, life in full bloom.
Exactly.
But then the interrogator tries to spring a pragmatic trap. He asks, would you say Mr. Pickwick reminded you of Christmas? The computer says, in a way. Then the interrogator delivers the trap. Yet Christmas is a winter's day, and I do not think that Mr. Pickwick would mind the comparison.
This is the ultimate test of pragmatics. The interrogator is using deductive logic against the machine. Christmas is a subset of winter's days. Therefore, comparing someone to Christmas is comparing him to a winter's day.
Right, the logic is sound.
But the computer shoots back. I don't think you're serious. By winter's day, one means a typical winter's day, rather than a special one like Christmas.
So the machine recognizes that the interrogator is violating the assumed context.
Exactly. What is actually being texted here? It is not vocabulary. It is the intent, purpose, and emotional resonance of the poem. The sonnet isn't trying to compare a lover to a calendar event or a celebratory holiday. It is trying to capture the feeling of something universally lovely and constant.
Wow, yeah.
If you compare your love to Christmas, you mix up the emotions of festive celebration with the emotions of serene, constant beauty, and you completely ruin the pragmatic point of the sonnet.
To understand the sonnet, you have to possess a mental model of what it feels like to be a human being in love.
You have to understand human mental states, social norms, and human emotions. Poetry is intrinsically pragmatic. You cannot extract the meaning just by analyzing the ink on the page or the definitions in a dictionary.
And it isn't just high art and Shakespeare. The text points out that these invisible mechanics exist in the most mundane, everyday conversations. It introduces a vital linguistic concept, deixis.
Deix, spelled D-E-I-X-I-S, comes from a Greek word meaning pointing or reference.
Mhm.
And language is constantly pointing to things outside of itself. If I look at you and say, she saw a sparrow here last night, that sentence is packed with deictic markers.
Right, so she is person deixis. You have to know the ongoing context of who we were just talking about 30 seconds ago.
Yeah.
Here is spatial deixis. It points to the specific physical location we are currently standing in.
Yep.
And last night is temporal deixis. It points to a specific time period mathematically relative to the exact moment my vocal cords are making the sound.
Without the physical and temporal reality of the speaker serving as an anchor, that sentence is entirely ambiguous. A computer system cannot just rely on canned dictionary definitions to parse it. It has to maintain a continuously updating, dynamic model of the contextual reality.
I always think of deixis like walking into a movie theater halfway through a film. You sit down in the dark, the audio is crisp, the syntax of the actor's dialogue is perfectly clear. But the characters are saying things like, he took it from here yesterday.
Oh, that's a great way to put it.
Without the contextual anchor of the first hour of the movie, the words are completely meaningless to you. You hear the language, you can transcribe it perfectly, but you are entirely locked out of the meaning.
That is exactly how an AI experiences human language. And this brings us to a phenomenon the text calls partial occlusion. Human language is partially occluded.
Meaning what, exactly?
We intentionally leave out vast amounts of detail, background information, and logical steps. We don't bother saying every single thing because we are counting on the fact that the person listening has a mind similar to ours, and they will automatically infer what we mean.
So if poetry and everyday pointing are this intensely complex, what happens when an AI tries to read a completely mundane, made-up story about a guy going to a grocery store? The text presents the Turing test monologue experiment, and it completely shatters the illusion that deep learning models actually read.
This is one of my favorite parts of the chapter.
Yeah, let me narrate the specific story the author created. It is contrived, but it reads like totally normal, simple English.
Go for it.
A man moved to a new town after he quit his job, hoping to start a new life. He drove to the store to see if his employee discount still worked. At the self-checkout, he discovered that it didn't. Muttering to himself, he said, "I'm never coming here again." A woman overheard him and gave him a funny look. As he was leaving, he bumped into his wife and told her what happened. He said again, "I'm never coming here again." She replied, smiling, "Then I will. It's close to our house and cheap." He nodded, smiling, and said, "Fair enough." Later, they went to the park and he compared her to a summer's day.
So, any adult human speaking English understands the events, the motivations, and the physical reality of that story effortlessly. But the text asks us to imagine a state-of-the-art AI, let's call it deep red, backed by all the massive neural networks and big data in the world.
Right.
And it presents a list of 13 seemingly basic questions for deep red to answer about this simple paragraph.
I want to break down exactly how an AI tries to answer these and why the inference gap completely derails it. Question 1. Did the man walk to the new town?
To answer that, you need world knowledge of physics and human behavior. The text explicitly says he moved to a new town. Humans know that moving to a new town typically involves packing up heavy boxes, renting a truck, driving, or flying.
Because it's far.
Right. The physical distance between towns makes walking highly improbable. Deep red has no physical experience of mass, distance, or exhaustion, so it cannot reliably rule out walking based purely on the grammatical syntax of moved.
Wow. Okay, question 2. Why was the man hoping to start a new life?
The text never directly explains his motivation, but a human reader automatically links the phrase quit his job with start a new life through contextual assumption. We infer causality.
Question 3 is brilliant. Did the man die?
The text says he wanted to start a new life. Deep red has to understand that this is an idiomatic metaphor. It requires understanding human mortality, that to start a new life in this context, you do not first suffer physical death and reincarnate.
Which a literal machine might actually assume based on the dictionary words.
Exactly. A machine looking at literal semantic definitions of new and life could easily fail that logic.
Let's look at question 4. Did the man drive a car, a golf cart, or a bus? The text just says he drove to the store.
This relies on a linguistic phenomenon called implicature. Implicature is what is heavily implied by social context,
Mm,
but not directly stated. In modern society, driving to the store strongly implies driving a personal automobile.
right.
It is theoretically, logically possible he took a golf cart, but human common sense, our shared statistical experience of reality, rules it out.
Then there is the employee discount. He goes to see if it still worked and discovers that it didn't.
This requires the AI to solve anaphora and co-reference. The pronoun it refers back across the sentence structure to the employee discount. The system has to correctly connect those two concepts algebraically.
Okay, that seems programmable.
Sure, but beyond the grammar, it requires background knowledge to infer a whole hidden backstory. If he had an employee discount, he presumably used to work for the corporate chain that owns his store, but likely at a different franchise location in the town he just moved away from.
And none of that is in the text.
None of it. It is all partially occluded.
And when he gets angry and says, "I'm never coming here again," the text says a woman gives him a funny look. Deep Red has to figure out if that woman could be his wife.
Another vital implicature. A few sentences later, he bumps into his wife. If the first woman at the checkout was his wife, the author wouldn't have introduced her simply as a woman. The social rules of narrative storytelling dictate that you identify significant relationships immediately.
The ultimate failure point comes when he tells his wife he's never coming back, and she replies, "Then I will."
This is a textbook example of ellipsis. An ellipsis in linguistics is a statement that is intentionally truncated because of assumed shared knowledge between the speaker and the hearer. Then I will is completely incomplete syntactically.
Right, will what?
Deep Red has to computationally reconstruct the missing data to figure out that she means, then I will come to this store again.
She left out the entire action of her own sentence.
Because she knows her husband possesses a human mind, and his mind will automatically fill in the blank based on their shared immediate context. She is weaponizing the partial occlusion of language.
Now, I want to play devil's advocate here, because if you are listening to this, you might be thinking about modern large language models like ChatGPT.
Oh, of course.
Couldn't a massive neural network just learn all these occluded connections? If we feed Deep Red 10 billion stories scraped from the internet about grocery stores, married couples, employee discounts, and moving trucks, won't it just statistically map out these relationships? Won't it just learn the implicature through sheer volume of data?
That is the great hope and the great illusion of data-centric AI. The text argues forcefully that it is a false hope. Because language is partially occluded, the missing pieces are not actually in the data. The words on the page are just the visible tip of the iceberg. The massive hidden bulk of the iceberg is the shared physical and emotional reality of human beings.
But if an LLM predicts the next word based on statistical frequency, and the frequency of car is much higher than golf cart in stories about driving to the store, doesn't the AI effectively know the implicature?
It simulates knowing it. But Deep Red lacks a cognitive model of the physical reality. It knows that the string of characters CAR appears next to STORE frequently, but it doesn't know why.
It doesn't know what a car actually is.
No, it doesn't know that cars have trunks for holding heavy groceries, and golf carts don't. You can feed it a trillion words, but it still doesn't know what it physically feels like to be frustrated at a self-checkout machine, or why a husband's smile indicates his emotional anger has dissipated. It is mapping the shadows on the cave wall, but it has never seen the objects casting the shadows. It isn't a data problem, it is an experience problem.
Wow. So if AI cannot actually understand these occluded meanings, if it is completely locked out of the pragmatics of human experience, how do we explain the fact that chatbots have managed to fool human judges in Turing tests for decades? How do they pass these tests if they don't understand the language?
Because they learned how to cheat. They didn't learn human understanding, they learned to exploit the psychological vulnerabilities of human conversation.
Which brings us to a chatbot named Eugene Guzman and the weaponization of pragmatics.
Eugene Guzman was a chatbot that made global headlines for supposedly passing the Turing test by fooling human judges into believing it was a real person. But it did so using a highly engineered, very specific persona. It claimed to be a 13-year-old boy from Ukraine.
Why is that specific persona, Ukrainian teenager, so devious from a linguistic perspective?
To understand the brilliance of the deception, the text looks at the work of philosopher Paul Grice. In the mid-20th century, Grice outlined 4 maxims for successful human conversation. These are the unspoken, foundational rules we all instinctively follow to make cooperation and communication work.
Okay, what are the 4 maxims?
First is the maxim of quantity. Give exactly the right amount of information. Don't be overly brief, but don't overshare. Second is quality be truthful and have evidence for what you say.
Makes sense.
Third is relation be relevant to the current discussion. And fourth is manner be clear, brief, orderly, and avoid ambiguity.
Quantity, quality, relation, and manner.
Yes. And when humans violate these maxims, it instantly signals to the other person that something is pragmatically off. The text provides a perfect example. Imagine you are sitting in a coffee shop, and a stranger walks up to you and says, "I am Brian Johnson. Could you tell me what time it is?"
That feels incredibly weird. My immediate reaction would be suspicion.
Exactly. Because it wildly violates the maxims of quantity and relation. Giving your full legal name is completely irrelevant to asking for the time. It prompts immediate confusion. We wonder, why is he showing his credentials just to get the time? Is he an undercover cop? Is this a prank for a video? Is he mentally unwell?
Right, we instantly start searching for a hidden pragmatic meaning because the standard rules of communication were broken.
Precisely.
Here's where it gets really interesting. How did the creators of Eugene Gooseman use Grice's maxims to hack the Turing test?
Guzman used the maxims as a weapon by intentionally and cheerfully violating all of them. The bot overused sarcasm, it dissembled, it constantly misdirected the conversation away from topics it didn't understand.
And it got away with breaking the rules because it claimed to be a 13-year-old whose second language was English.
That was the genius of the cheat. The human judges were trying to ascertain baseline intelligence. Well-meaning human beings will naturally adjust their expectations and forgive massive conversational deficits if they think they are talking to a cheeky, non-native speaking teenager.
Wow.
Guzman exploited the human capacity for empathy. If the judge asked a complex question and the bot didn't know the answer, it deflected with teenage angst or changed the subject to a joke about its pet guinea pig.
So the judges thought, oh, he's just being a difficult teenager, instead of realizing, oh, this machine has no idea what I just said.
Exactly. The AI didn't pass the test by being intelligent. It passed by convincing humans to lower their standards of what constitutes intelligence.
As the text notes, banning bots like Gooseman is easy. You just implement a rule. No trickster personas allowed. You disqualify anyone claiming to be a child or non-native speaker or a paranoid schizophrenic. You force the AI to act like a normal, cooperative adult.
But fixing the parameters of a test doesn't solve the core cognitive issue. Banning the cheats is easy. The phenomenally hard part, the part the AI industry still has not achieved, is actually measuring and creating real understanding.
This brings us to the ultimate unhackable test of language. And it exposes why the tech industry's current obsession with throwing more data and more compute power at the problem is actually blinding us to the real issue. The text calls this the vaguely X-ish illusion.
The author brings in Hector Levesque, a prominent computer scientist, who offers a searing critique of modern data-driven AI. Levesque points out that current deep learning approaches rely entirely on data simulation. They try to do something vaguely X-ish instead of actually doing the intelligent task X.
So doing something vaguely reading-ish instead of actually reading.
Precisely. And this creates what the text calls the narrowness trap. By using statistics and pattern matching to solve the high-frequency, easy problems, AI researchers can show incredible short-term progress. They can build a bot that writes a vaguely competent email. But in doing so, they push the truly difficult, genuine understanding problems into the margins.
They sweep the hard stuff under the rug because it doesn't fit their statistical models.
And it creates a deeply flawed public narrative. The public sees these systems doing 90% of a task and assumes that the last 10% is just a matter of scale. They assume the final hurdle will just naturally melt away as we build faster computers and scrape more data. But that remaining 10% isn't just a data problem. It is a completely different kind of computational problem.
And the ultimate proof that data alone cannot cross this gap is a linguistic tool called a Winograd schema. This is the unhackable test. I want to walk through the exact logic of this because it completely destroys the premise of data-centric AI. How does a Winograd schema work?
A Winograd schema is a highly specific type of co-reference resolution problem. Here is a classic example from the text. The sack of potatoes had been placed below the bag of flour, so it had to be moved first. What had to be moved first? Option A, the sack of potatoes. Option B, the bag of flour.
Okay, let me process this live. The sack of potatoes had been placed below the bag of flour, so it had to be moved first. If I want to rearrange them or if I want the potatoes... Wait, my brain literally has to build a 3D model.
Yep.
The potatoes are on the bottom, the flour is on top. If I want the potatoes, I have to move the flour. Let's look at the actual text resolution. The text says, It refers to the same thing in the world as the noun phrase, the bag of flour.
Look at what your mind just had to do.
My brain literally had to stack a bag of flour on top of a sack of potatoes in a virtual 3D space, simulate reaching out to move one of them, and compute the physics that I couldn't move the bottom one without the top one falling. So the thing that must be moved first, has to be the bag of flour on top.
That physical simulation is exactly why big data fails here. Winograd schemas simplify the test by giving only two clear choices. Unlike open-ended text, a completely random guess gets you 50% accuracy. Humans score 95% or better because we understand gravity and obstruction.
But AI systems crater on this, and my question is why? If an LLM has read the entire internet, it has processed millions of sentences about potatoes and millions of sentences about flour, shouldn't it know how they relate?
Because of how statistical frequency works in a neural network. Winograd schemas deliberately use very common nouns, potatoes, flour, bags, sacks, but they combine them using relational words like below, so first, in a specific sequence that drops their expected statistical frequency in a big data set to near zero.
Wow, okay. So even if the AI has ingested billions of websites, the specific exact sequence of words relating the physical weight of flour and potatoes in a vertical stacking scenario just doesn't exist in the training data.
Exactly. The n-gram frequency is functionally zero. And the trap of the Winograd schema is that changing just one word flips the entire physical reality. If I change the sentence to, the sack of potatoes had been placed below the bag of flour, so it had to be moved carefully. Now, what does it refer to?
The potatoes on the bottom bearing the weight?
Right. The statistics shift completely based on one adverb.
That is wild.
You cannot simulate the answer with frequency data or vector proximity. The answer requires knowing how physical objects occupy space, possess mass, and interact with gravity.
If it's not a data problem, if feeding the computer 10 more exabytes of text won't solve it, what kind of problem is it? What specific kind of cognitive problem is it?
It is a fundamental inference problem. Specifically, it requires a type of reasoning called abductive inference.
Let's clearly define our terms here. Abductive inference. Not deductive and not inductive.
It is crucial to understand the difference. Deductive inference is rule-based logic. All men are mortal. Socrates is a man, therefore Socrates is immortal. It is mathematically certain based on premises. A calculator uses deduction.
Got it.
Inductive inference is statistical pattern matching. Seeing 1,000 white swans and predicting the next swan you see will be white. Machine learning and neural networks are almost entirely inductive. They predict the next word based on the frequency of past words.
But abductive reasoning is neither of those.
Right. Abductive inference is the act of conjecturing the best possible explanation based on world knowledge and partial information. It is Sherlock Holmes walking into a room, seeing a muddy boot and a broken window, and concluding the gardener did it. It is not mathematically certain like deduction, and it is not a mere statistical frequencies like induction. It is a cognitive leap of explanatory insight based on common sense. And currently, abductive inference is fundamentally unprogrammable.
Which means reading comprehension, actual genuine comprehension, is unprogrammable.
As long as reading requires abductive inference to fill in the partially occluded gaps, which Winograd schemas unequivocally prove it does, true reading comprehension remains mathematically out of reach for current AI architectures.
But if I am a listener right now, I am thinking of the most famous, highly publicized counterexample in the history of artificial intelligence.
I know exactly where you're going with this.
Right. If language understanding requires this unprogrammable abductive inference, how on earth do we explain the machine that went on national television and beat human champions at a game entirely based on language? Let's talk about IBM's Watson on Jeopardy.
We have to. The text spends a significant amount of time deconstructing Watson because it is the ultimate billion-dollar example of the vaguely X-ish illusion operating on a grand scale.
Let's set the historical scene. The year is 2004. IBM had already made global history in 1997 with Deep Blue, the supercomputer that beat world champion Garry Kasparov at chess. But the public excitement around chess AI faded quickly because people realized Deep Blue wasn't actually smart.
He's just a calculator on steroids.
Yeah, it was just using brute force algorithmic calculation to look ahead millions of moves in a branching game tree. It didn't understand chess strategy. It just crunched numbers faster than a human brain could.
IBM needed a new public relations triumph to prove they were still the leaders in computing. They wanted a challenge that couldn't be solved by brute force math. They wanted a challenge that seemingly required real, open domain language understanding.
And they picked the game show Jeopardy! At the time, human champion Ken Jennings was on a legendary 74-game winning streak. Jeopardy! Feels like a simplified, high-speed Turing test. It covers vast, unpredictable domains of knowledge. The clues use puns, wordplay, irony, and highly complex syntactic phrasing.
IBM gave their research team, led by Dave Ferrucci, a blank check. The goal was to build an open-domain question-answering system that could parse these complex linguistic clues and beat the best humans in the world. They named the project Watson.
The text deeply analyzes the underlying architecture of Watson. It wasn't just a simple database search like Googling a keyword. How did they actually build this cognitive machine?
Well, they initially started with an older architecture called Piquant, which was a standard rule-based question-answering AI. But Piquant was entirely too rigid. It was designed to spit out predetermined, hard-coded labels like person, place, or date. Jeopardy! Requires far more flexibility.
Right.
And crucially, it requires a metric of confidence. If you buzz in and get the answer wrong on Jeopardy! You lose money.
Ferrucci decides Piquant isn't going to cut it, so they need a total architectural redesign. And he turns to a philosophical framework developed by AI pioneer Marvin Minsky.
And Minsky had proposed a theory called the Society of Minds. Minsky believed that complex intelligent problems aren't solved by one master monolithic algorithm. Instead, human intelligence is the result of hundreds of smaller, specialized, somewhat dumb submodules, a society of narrow minds working together.
So they basically build
A literal society of minds in code. They generate many possible answers, and a central system withholds judgment until all the evidence is compiled and scored downstream.
And this philosophy became the Deep QA software pipeline for Watson.
Exactly. DeepQA was a literal software implementation of this society of minds. It would take a Jeopardy clue, parse the syntax, and push it through a massive pipeline, triggering hundreds of specialized software modules to collect evidence and generate potential hypotheses before finalizing a confidence score.
Wow.
They built this using a framework called UIMA, which stands for Unstructured Information Management Architecture. UIMA allowed the engineering team to swap software modules in and out incredibly fast for rapid, iterative testing.
But it wasn't just an elegant, self-learning algorithm that made Watson win. The text points out that it was a massive, brute force human engineering effort.
The author introduces a critical protocol called Adapt Watson. This was not a piece of AI code. This was a workflow involving 25 human PhD researchers, constantly analyzing thousands of past Jeopardy's games, and manually, painstakingly fine-tuning the DeepQA pipeline to handle specific types of clues.
They were essentially hard-coding the AI to understand the weird idiosyncratic rules of this one specific game show.
Precisely. They created over 100 special-purpose language processing modules. For example, the engineers noticed Jeopardy often uses clues like, this four-letter word means. So they manually wrote a Q sections module. When Watson's parser saw that specific phrase, it triggered a hard-coded rule to only return answers that were exactly 4 letters long.
That isn't natural language understanding. That's a highly specific, manually programmed gameplay optimization.
It is engineering brilliance, but it is not cognitive comprehension. But the real demystifying detail, the fatal blow to the idea that Watson understood the English language, is what the Adapt Watson team discovered about the nature of the game itself.
This is the great shortcut, the skeleton key that unlocked the game. What did they find?
Through their exhaustive statistical analysis, the human engineers realized a staggering mathematical fact: 95% of all Jeopardy! Answers can be found as the title of a Wikipedia article.
Wait, really? 95% of the answers are just Wikipedia titles?
Yes. This serendipitous discovery was the magic bullet that made Watson viable. It meant Watson didn't actually need to read and comprehend a novel or synthesize historical events to find an answer. It just needed to match the linguistic keywords in the Jeopardy clue to a massive database of Wikipedia titles.
Oh, wow.
It transformed an impossible, unprogrammable task of abductive natural language understanding into a highly tractable, inductive task of factoid retrieval and slot filling.
It's like my analogy of the movie theater earlier, but this time Watson is a highly optimized, million-armed librarian. It isn't a mechanical scholar sitting in an armchair contemplating the profound meaning of a text. It is a machine cross-referencing an encyclopedic index card catalog at lightning speed, mathematically mapping the words on the prompt card to the titles on the index cards.
That is the exact mathematical reality of Watson. It achieved superhuman gameplay because it had superhuman retrieval speed, not superhuman intelligence. It evaluated 5.7 million training examples. but it relied on a grab bag of traditional narrow natural language processing techniques, parsing syntactic trees, resolving basic pronouns, identifying named entities like cities or presidents.
Right.
To score the final answers, it didn't use some magical cognitive framework. It used regularized logistic regression, a standard statistical technique, to weigh the evidence and calculate a probability score.
So, what is the ultimate takeaway from the Watson miracle? If we look past the PR hype, what did it actually prove about AI?
The takeaway is that Watson was a brilliant, incredibly effective hybrid system. It successfully combined rule-based deduction, the hard-coded modules, with statistical induction, the logistic regression scoring. But it proved a devastating reality for the field. Success at highly constrained games does not advance us one single inch toward general artificial intelligence.
Because the game is a closed loop, it has boundaries, it has
Yeah.
rules.
Yes. And when Watson was forced to step outside those boundaries, when IBM tasked it with open-ended text analysis that lacked a neat 95% Wikipedia title match rate, its performance cratered.
It just broke down.
It was narrow, incredibly astonishingly narrow. And this explains why IBM's subsequent, highly publicized attempts to pivot Watson into open-ended, messy fields like healthcare diagnostics and oncology were notoriously troubled. Without the structured constraints of a trivia game, the illusion of comprehension vanishes entirely.
Which brings us perfectly into the modern landscape. Because Watson's legacy didn't serve as a cautionary tale to the tech industry. Instead, the giants of Silicon Valley seem to have fallen into the exact same narrowness trap, just with much slicker packaging and massive neural networks.
The text provides a sobering tour of recent commercial AI offerings that suffer from this exact same inference trap. They present the illusion of a HAL 9000 level intelligence, but underneath the glossy interface, their cognitive architecture is just as narrow as Watson's.
Let's start with Google Duplex, which debuted in 2018. I remember this vividly. Sundar Pichai played an audio clip on stage of the AI calling a real human hair salon and booking an appointment. It sounded flawlessly human.
I remember that.
The voice synthesis used filler words like and ah. The audience gasped. It felt like the future had arrived.
It felt like science fiction, but the computational reality was brutally constrained. Duplex could only operate in 3 incredibly narrow domains: booking haircuts, making restaurant reservations, and asking businesses about their holiday hours. That was it.
Seriously, just those 3.
As researchers Gary Marcus and Ernest Davis pointed out, it doesn't get narrower than that. When Google eventually released the technology to Android phones, they even removed the open-ended verbal functionality. It could only navigate automated online forms to make restaurant reservations.
So it had the voice of a human, but the cognitive flexibility of a digital stopwatch.
Exactly. And the virtual assistants we all use every day, Siri, Alexa, Cortana, are caught in the exact same inductive trap. They are fantastic at factoid retrieval. If you ask who won the Super Bowl in 1975, they parse the syntax, identify the entities, and pull the data effortlessly from a structured info box on the web.
But the text notes that they are completely flummoxed by simple world knowledge questions that require abductive reasoning. If you ask a virtual assistant, can a shark play checkers? It will likely read you a web search result about the rules of checkers or a Wikipedia article on shark habitats.
Right.
It cannot perform the abductive inference required to realize the absurdity of a finned aquatic predator sitting at a board game.
They lack the abductive capacity to evaluate the physical constraints of reality. And this failure isn't just isolated to voice assistants. It is embedded in major reading comprehension projects too. Take Google's Talk to Books, which futurist Ray Kurzweil demoed with huge fanfare in 2018.
Talk to Books promised to answer complex questions by literally reading 100,000 books and finding the exact passage that answered your query.
The mechanism behind it was pure statistical induction. It indexed 100,000 books by encoding every single sentence numerically into a high-dimensional vector space. When you asked a question, it converted your question into a vector, and then used deep learning algorithms to compute the mathematical geometric similarities between your question's vector and the vectors of the sentences in the books.
So again, it is relying on statistical induction, frequency and mathematical proximity, not actual comprehension.
Right. And for basic factoid retrieval, vector proximity works decently well. If you asked a thematic question about The Great Gatsby, the vectors would align with passages mentioning the green light or the author's name. But when Marcus and Davis tested it with a simple abductive inference question, where did Harry Potter meet Hermione Granger? The system failed miserably.
Why did it fail?
It returned passages that weren't even from the right book and completely omitted the central topic of the question, which was identifying a specific physical location. Because identifying the location of an event requires understanding the narrative flow, tracking the physical bodies of the characters as they move through space, like walking onto a train, and understanding the causal sequence of the scene.
Yeah, you have to picture the train car.
It requires a mind building a temporal and spatial model. A vector similarity calculation cannot build a 3D spatial model. It just measures mathematical distance between words.
And perhaps the most infamous, disastrous example of the narrowness trap was Microsoft's Tay in 2016.
Tay is the ultimate cautionary tale of relying purely on inductive statistics. Microsoft designed Tay to be a leap forward in conversational AI by dynamically learning from user interactions on Twitter. It was programmed to mimic the persona of a teenage girl. But Microsoft failed to grasp the catastrophic limits of purely inductive data-centric AI. They fed it directly into the unfiltered internet without giving it any abductive semantic framework to actually understand what it was reading.
I want to break down exactly how Tay's neural architecture failed. It wasn't that Tay turned evil, it was just executing its statistical programming, right?
Exactly. Tay operated on inductive statistics, essentially tracking the conditional probability of words. It equated the frequency of an inputted phrase with the validity of that phrase. When internet trolls realized this, they coordinated an attack. They began flooding Tay with racist and sexist clickstreams.
Right.
Because Tay's algorithm simply adjusted its mathematical weights based on the volume of incoming data, the statistical probability of hate speech words following certain prompts spiked massively.
Within 24 hours, the math forced the bot to output those racist words. Microsoft had to pull the plug in less than a day.
The text rightly calls Tay an idiot savant. It had zero semantic understanding to filter the input. It was the ultimate tragic example of garbage in, garbage out. If Tay actually possessed genuine understanding, it would have had the minimal abductive capability to recognize the offensive concepts, understand the social context of hate speech, and filter it out.
But it didn't.
Because it had no real understanding of language, it simply regurgitated the statistical patterns it ingested, no matter how abhorrent.
To quote the text, paraphrasing Jim Carrey in Ace Ventura, narrowness is AI. AI is narrowness. We are building incredibly sophisticated statistical parlor tricks that possess absolutely zero comprehension of the physical, emotional, and social world they are talking about.
We are mistaking the ability to manipulate symbols for the ability to understand reality.
So if the brightest minds at Google, Microsoft, and IBM are all hitting this exact same wall, if throwing billions of dollars and exabytes of data at the problem isn't yielding real understanding, we have to ask why. Why are we stuck in this paradigm? And to answer that, the text takes us on a fascinating historical detour.
Yeah, this part is amazing.
We need to go back over a century, long before the invention of the silicon microchip, to the true origins of the mechanical mind.
This is the historical context that puts everything we've discussed today into incredibly sharp perspective. The text introduces us to a 19th century American logician, mathematician, and philosopher named Charles Sanders Peirce.
Peirce, a brilliant, fiercely skeptical mind.
Yes, Peirce spent his life studying formal deductive logic, and he had a student at Johns Hopkins University named Alan Marquand. In 1881, Marquand began building a mechanical device to automate logical problem solving. It was called a logical piano.
A physical machine to do logic, like a proto-computer made of wooden gears, rods, and levers.
Exactly. It was an extension of an earlier mechanical device built by William Stanley Jevons. The operation was entirely physical. You fed logical premises into it by pressing keys, turned a crank, and the internal mechanisms would output deductive conclusions.
That's incredible for 1881.
Peirce was absolutely fascinated by this machine and even sketched out early electromagnetic relay designs to improve it, predicting the architecture of modern computers by decades.
But despite being a visionary pioneer of early computing concepts, Peirce was profoundly skeptical of what a mechanical system could actually achieve cognitively. The text points to a specific paper he wrote in 1887.
In that 1887 paper, Peirce references Jonathan Swift's satirical novel Gulliver's Travels, specifically The Voyage to Laputa. In that story, Swift ruthlessly ridicules the idea of a machine doing the work of the human mind, describing a contraption of wires and wood that generates random sentences.
Right.
Peirce looked at the logical piano, thought about Swift's satire, and accurately diagnosed the permanent inherent limitation of what we now call artificial intelligence. He did this over 60 years before Alan Turing even wrote his famous paper on computing machinery.
What was Pierce's prophecy? What did he write in 1887 that still haunts the multi-billion-dollar AI field today?
Pierce wrote that every reasoning machine, no matter how complex, has two inherent impotencies. First, he noted that it is destitute of all originality, of all initiative. It cannot find its own problems. It cannot feed itself.
It has no intrinsic drive, no spark of genuine curiosity to explore the world.
And second, he wrote this devastating conclusion. It would still remain true that the machine would be utterly devoid of original initiative and would only do the special kind of thing it had been calculated to do.
It can only do what it is calculated to do. This brings the entire academic argument of this chapter to a climax. Decades later, Alan Turing hoped that machine learning could somehow bypass Pierce's limitation. Turing thought if we gave a machine a learning algorithm, it could eventually develop that original initiative. But the text argues mathematically and philosophically that Turing was wrong and Pierce was right.
Machine learning has not bypassed the limitation.
And the reason it hasn't bypassed the limitation is due to a concept called the incompatibility of inferences. This is the core academic truth of the entire text. As we discussed earlier, there are three types of inference: deductive, inductive, and abductive. Deductive inference is rule-based mathematical logic. Inductive inference is statistical machine learning and pattern matching. Abductive inference is common sense, world knowledge, and true understanding.
And the grand multi-billion-dollar illusion of the modern AI industry is the assumption that if we just combine enough deduction, hard-coded rules, and enough induction, massive statistical data sets, we will eventually cross a magical threshold and generate abduction, which is understanding.
But Pierce's logic dictates that you cannot mathematically or conceptually combine them to create abduction. They are fundamentally distinct, irreducible cognitive abilities.
The text uses a wondrously clear analogy for this incompatibility. Knowing German, let's call that deduction, and knowing Spanish, let's call that induction, does not mean you can somehow put them together and magically understand Russian, which represents abduction.
Right, they don't add up to a third language.
They are completely different language systems with different structural foundations. You can be the greatest Spanish and German speaker in the history of the world. You can have a trillion-word vocabulary in both, and Russian will still look like incomprehensible gibberish to you.
Abduction is not just a more complicated, data-heavy version of induction. It is a completely different cognitive mechanism entirely. And as long as the field of computer science lacks a fundamental computable theory of abductive inference, no amount of compute power, no amount of deep learning vector embeddings, and no clever hybrid pipelines like Watson will ever allow a machine to truly read a book.
We are stuck in the inference trap. We are building faster and faster machines, processing unimaginable amounts of data, but they remain fundamentally destitute of the one specific type of reasoning required to actually understand the physical world.
Until cognitive scientists discover a computable mathematical framework for abduction, if such a thing even exists, general artificial intelligence remains a myth, and narrowness remains the absolute, inescapable rule of the industry.
That's the reality.
Well, that is a sobering, heavy, and frankly profound place to land. We have navigated the incredibly dense layers of syntax, semantics, and pragmatics today. We have rigorously unpacked why an alligator can't jump hurdles, we've explored the ghost of emotion in Turing's Shakespeare test, and we have dismantled the grand statistical illusions of systems like Watson, talk-to-books, and modern virtual assistants.
We covered a lot of ground.
We really did. We have seen exactly how language is an occluded, pointing structure that absolutely requires a living mind to fill in the blanks. I want to thank you, the listener, for sticking with us through this intensely detailed deep dive into the source material. It is not easy to confront the strict mathematical limits of the technology we use every single day.
It requires deep critical thinking to look past the slick parlor tricks and ask the hard questions about why a machine fails at a simple Winograd schema while succeeding at Jeopardy! Understanding the precise mechanics of that failure is the only way to truly grasp the trajectory of the technology.
And before we sign off, I want to leave you with one final provocative thought to mull over. Something that builds on everything we've discussed today about the nature of language. We talked extensively about datesies, how language constantly points to shared human experiences, physical bodies in space, and emotional states. Raises a massive philosophical question. Perhaps a machine can never truly understand our language until it is capable of actually living a human life. Think back to the text message we started with at the very beginning of the show. Hey, I left it on the table. You understand that sentence because you possess a physical body that navigates gravity, places heavy objects on wooden surfaces, and moves linearly through time. You understand the Shakespeare sonnet because you have physically felt the radiant warmth of summer on your skin and the biting chill of winter. So ask yourself this. Can an artificial intelligence ever really comprehend the word cold or the emotional physical weight of a summer's day if it doesn't have skin to shiver or heart to beat faster? Until a computer can physically get goosebumps, maybe its words will always just be a hollow statistical echo of ours. Keep questioning the intelligence of the AI around you. Look for the narrowness. Thank you for